So today we will start with the discussion of complex integration. Okay. So in this chapter, omega will be denoted as an open set in C. Okay, so this is a notation, and we recall that an analytic function on an open subset omega is a differentiable complex function defined on omega. Okay. And in the literature, an analytic function on an open subset omega is also called a holomorphic. Okay, a holomorphic function on omega. Okay. So that the set of all analytic function or holomorphic functions on the open set omega will be denoted as H of omega. So H of omega is the set of all holomorphic functions defined on an open subset of the complex plane. Okay. So this is the notation will be used in this chapter as well as the following chapters. Okay. All right. In the first section, we will consider the line integrals. Okay. So first of all, to define line integral, we will consider some spatial subset of in the complex plane. So an oriented, right? An oriented curve, so that all the curves considered in this semester will be oriented. Okay. So an oriented curve in the complex plane C, okay, right, is a continuous. It's a continuous mapping gamma of a finite closed interval alpha, beta in R into C, and here, because of it's oriented, so alpha will be less than beta. Okay, so a curve. So this is alpha, this is beta, and a point T, a gamma goes to here, so that So this is gamma alpha. This is gamma beta. And it is co-oriented because that the parameter t, okay, will start from alpha to beta in this finite cost interval. And as t increased, then the corresponding point will move from this endpoint gamma alpha to the other endpoint gamma beta. So that this is the direction of movement. Okay. So instead of saying the image, all right, the point set in the complex plane, we define curve as a mapping itself. Okay, as a mapping itself. Okay, to describe the movement of the point as the parameter t move from alpha to beta. Okay, so we say that you can see that the image of this mapping, which is called the conditional curve, right? If we usually we think about the point set here is a curve. Okay, it's the traditional one, but to orient the curve, so we will actually define oriented curve as a mapping here, and so that the image, okay, will be denoted, which is just the of alpha beta. Okay. Will be denoted as gamma star. Okay, so gamma star will be the set of T. Okay, so it's a subset of the complex plane. Okay. All right. Now, so this curve, and if the two endpoints are equal, so if the two endpoints are equal, then gamma is called a closed curve. Okay, so in this case, so a closed curve would be, for example, okay, so it's start from here and go to there. Okay, and actually, a curve can be so that we know T will be called parameters of the curve. Okay, the gamma star. Okay, so gamma star the image. Okay, so we used that the mapping. Okay, to orient the image here. All right, and so it's kind of parameterization of gamma star, right? And gamma star can be reparameterized by another mapping. And so we have to define such a reparameterization, right? So suppose that phi from alpha 1 to from this finite closed interval to that finite closed interval, right? Be continuously differentiable one-to-one mapping and onto of finite closed interval alpha 1, beta 1 onto another finite closed interval okay. Right, so okay, and it's clear that the inverse function, the inverse or mapping from alpha beta onto alpha 1 beta 1 is also continuously differentiable. Okay, so we know that it's also continuously differentiable. Okay, so oh, by the way, I forgot to such that alpha is equal to phi alpha 1 and beta equal to phi beta 1. Okay, so the orientation is same, right? So it's going up. Okay, so when the point t is from, say t is from alpha 1 to beta 1, then the image will go from alpha to beta. Okay, so it will preserve the direction of the order. Okay, preserve the order of elements in these two finite closed interval. Okay, so I'm sorry I forgot to put this one. Okay. Right. All right. So so now we have so originally we have t here. So it's go to say here. Okay, this is gamma, right? And we have one-to-one mapping, okay, from alpha 1 to beta 1. So this is x here, okay. And now the composition, Okay, we define the composition to be gamma 1. Okay, so this gamma and phi, yeah. Okay, now, because phi is differentiable, so of course phi is continuous. And gamma is continuous, so the composition of two continuous functions is also continuous. Okay, this is also continuous. Right. So that so things gamma and phi are continuous mapping. Gamma 1 is continuous. Oh, and also okay, so it's also continuous. Okay. Okay, and then it's a curve in C. Okay. All right, and it's clear that the image of gamma 1 is equal to the image of gamma. Okay, right. So because phi is 1-to-1 on 2, okay, so that they have the same image here. Okay. All right, so we call gamma 1 a reparametrization of gamma. Okay. So the parametrization will be established if two parameter intervals, all right, can be associated by a continuously differentiable 1-to-1 mapping. Okay, continuous differential. Okay. Any questions? Right. And conversely, since we can see that the gamma actually is gamma 1 and involve the inverse. Okay? Okay, because when you composite with the inverse of the phi, you will see that here. So and we know the inverse mapping by phi is also continuous differentiable. Okay, 1-to-1 and onto mapping. So that we can say gamma is a reparametrization of gamma 1. Okay, and so we call, in this case, we call that gamma and the gamma 1 equivalent. So actually, the parametrization is actually an equivalence relation, okay, between curves, okay, between curves. So, and the equivalent curves will have the same images, okay, and has the same orientation, right? So not only they have the same image, but also they have the same orientation, okay. And the reason is here, it's very important, is that this mapping phi preserve the order, okay, preserve order. So it's very important to know here, so that the orientation is preserved. All right, now, but in complex integration, we will consider oriented path. All right, so we'll consider oriented path. And oriented path, X, right? So something like, so for example, the polygon, something like that, okay? So you can establish, so if we have a polygon like this one, actually we can establish a curve, okay? Means that a continuous mapping, okay? Such that its image is just this polygon, okay, in the complex plane. And but as you can see that if we establish such continuous mapping, it is not differentiable at a corner point here. Okay, this is obvious. All right. Okay, but it's very common to consider a curve like this one. All right. So so we will define that. We will say this is a path, at least that. So an oriented path is piecewise continuously differentiable. Oriented curve. Okay, so even though this curve, okay, so even though so even though that the curve is not differentiable at every point, but at least it is piecewise continuous differentiable, right? Because that in this range, right? So is actually you can divide the parameter interval into 3 parts, okay? So that you have T1 and T2 here, okay? And so you can see that in this interval, right, it's just a line segment, so that it's differentiable and continuous differentiable in this subinterval. And from T1 to T2, corresponding to this line segment, and it's also continuous differentiable. And the other, so this one, in each piece, you see the mapping is continuously differentiable. Okay, so such a curve, such an oriented curve, will be called oriented path. Okay, and a closed path, right, is a closed curve okay, which is the path. Okay, and we call gamma and gamma 1 equivalent passes if gamma and gamma 1 are equivalent curves which are passes. Okay. All right. So okay. So this is the setup that we will use when we define the line integral. Okay. An important example would be, I can say, all right, so if we select a point z sub 0, then the R is positive. Now the path, right, defined by gamma t, which is z0 plus REI 2 pi t, for the parameter is in 0 for 1. Okay, so that so we have this is z0. Okay, and then this is the radius r. So this is circle here, and from 0 to 1, gamma. Okay. Okay, and this point is actually gamma 0 equal to gamma 1. Okay. So the path, right, is called positively oriented circle, okay, with the center z sub 0 and the radius r. And let's see the orientation of this path, all right, in the image. Okay, so the image itself, the image actually is just the circle, right, with the center z sub 0 and radius r here. Okay. And you can see that the orientation is counterclockwise, and usually we denote orientation counterclockwise to be positively oriented. Okay, so this is positive oriented here. Okay, okay. And it's a simple, a very useful parameterization of this circle, right? So the image is a circle here, and now with this parameterization, that this the gamma here define a positively oriented circle. Okay. second example. So if Z1 and Z2 are 2 points in the complex plane, the path, all right, so suppose this is Z1 and this is Z2 here. Okay, now this is the line segment. Okay, so the path. So now we want to orient this segment, and the way to do. Okay. So now we want to orient to show that this curve is starting from Z1 and go to Z2. Okay. So how do we do that? Well, this is Z1 plus Z2 minus Z1 times T. Okay, and T is in Z1. Okay, so you can see that that the line segment can be oriented, all right, by this path, okay, by this path. Okay, so it's called the oriented interval or oriented line segment, all right, and denoted as Z1 to Z2. Okay, so we write okay, as an interval, right? But actually Z1, Z2 are complex numbers. Okay, all right, and so this notation shows that it's a line segment, all right? It's a line segment. And oriented from Z1 to Z2. So it starts from Z1 and at Z2. Okay. And we use this one, it's a representation of this mapping. Okay. So the oriented line segment, right, is actually described by this path. Okay, by this path. Its image is a line segment, of course, the image. But if you consider only the image, you don't know the orientation at all, okay? Yeah, the orientation can be this way, right? Right. So, for example, you can have Z2 to Z1, right? So these two oriented line segments have the same image, right? They have the same image, but they have different orientation. So they are different paths, okay? Because they are different mapping, right? So which is different from this line segment, okay? So they are different. Any questions about? Yes, please. No, not necessary. Breathing, not necessary. Yeah. I can, for example, I can do the parameterization. So, for example, phi is from 0 to 2 pi and goes to 0, 1. Okay. So for x goes to t is equal to is divided by 2 pi. Okay, is that way? Yeah. Okay. So you can see that but phi under this is continuously differentiable and one-to-one and onto, right? Okay. So you can see here, and so gamma 1 is which is defined to be gamma, and but phi is here. Okay. Okay, and so that this is gamma by phi of x here. Okay, so this is gamma, and it's s to pi here. So this is z0 plus r e I s. Okay. So gamma 1 is here. This is function for x in 0 to 2 pi. Okay. So you can see this is indeed, and they have the same image here. It's just a circle, right? With center z sub 0 and the radius r here. But you can see these two intervals has different lengths, right? The length of this interval is 2 pi, but the length of this interval is 1 only. Okay. Other questions? I think the difference between different parameterization is the speed, right? The speed you have. Okay. If you use this parameterization, the speed is higher than this parameterization. Right. So this is the speed of gamma 1 is slow. Okay, because in one time unit you have to move one circle, right? One circle. But in here you take 2 pi minutes, right, to travel one circle. Okay, so the speed, if we use this parameterization, the speed is higher than the speed you use gamma 1. Okay. Other questions? Okay, so now so now suppose we have a gamma which is a path, okay, in complex plane, and f, all right, a complex function, okay, which is continuous on the image of gamma. Okay, the image of gamma. Right, and now, so the integral or the line integral sometimes, okay, of f over the path gamma is defined as the following way. So gamma f dz. Okay, so notation is here. The integral of f, all right, over the path gamma here, right? So this is just the notation. And this line integral is defined in terms of the parameterization. So it's gamma t and gamma prime t and dt. Okay. So we need a derivative, right? right? We need derivative. And we know for a path, then it is piecewise continuous differentiable. So that you can decompose this parameter interval into several pieces, right? Into several pieces. So in each piece, that the derivative exists and is also continuous. Okay, so you have continuous. So this is continuous function, and also this is a continuous function. Okay, and then so the integrand is a continuous function because by our definition, a path is a curve. So as a curve is a continuous function. Okay, and f is also, we assume, is continuous, right? So the composition, so this is a continuous function of t. Okay, and this is also a continuous function of t here. Okay. So the evaluation will becomes to so a maybe is t, we will say t0 and t1, and the f gamma prime t dt plus okay, and the f okay, right. So the evaluation of this integral, okay, can be decomposed into the evaluation of n. Okay, so if we can decompose AB alpha beta, sorry. Okay. Yeah. Okay. So that so here so that gamma is continuously differentiable on T I to T I minus 1 to Ti for I from 1 to up to n. Okay, because the path, the gamma, is piecewise continuously differentiable, so that we can that in each piece, gamma is continuously differentiable. Okay, differentiable. So that in each piece we have and so this is the evaluation of this integral. Okay, this is the evaluation of this integral, and each integral is a finite number value because this is continuous function. This is also continuous function. So a continuous function integrate over a finite interval is also we have so by the Riemann integral theory that it is a finite number. Okay. So this integral is well defined, and you really can evaluate it. Okay. Okay. So this is the reason why we consider path, because we need the derivative. Okay, we need the derivative in the definition. Okay. Any questions? Okay, now suppose that gamma 1 is equivalent to gamma, right? Now, since gamma 1 star is equal to gamma star, right? So F is also continuous okay on gamma 1 star. Okay. Right. And so the line integral of F, right, over gamma 1 x. So now we compute the line integral of F over gamma 1. So gamma 1 is equivalent to a gamma, right? We just assume that. Now, okay, so we compute this line integral of F over gamma 1. All right, and so we have by definition, right? So we have that. And but as we know, gamma 1 is gamma composite with bar phi. Okay. So gamma 1 prime is actually gamma prime bar phi times bar phi. So we will see here gamma prime, the derivative is equal to gamma prime of phi s, and okay, by the chain rule, right? By the chain rule. So now we have F and gamma 1. So this is gamma, and okay, so this becomes 2. All right, and gamma 1 prime, the derivative is gamma prime s. All right, and the phi prime s, and the ds here. Okay, and we define t to be by phi x. Okay, so that dt is phi prime x and ds. Okay, so we do the change of variable, right? So we let bar phi x to be t, and so the integrand alpha 1 goes to alpha, beta 1 goes to beta, and this is gamma of t. Okay, because this is t, and this is gamma prime of t, and this is dt. Okay. All right, so what? This is gamma. the line integral, right, by our definition. Right? Okay, and so if gamma 1 is equivalent to gamma, then they will have then their line integral, okay, will be the same. Okay. Any questions? Right. Okay, so we take a break. Okay. If you have any doubt about how do we define the line integral in this way, you can approximate this integration the following way. So that so you can think about if we go here, so we take the point here. Okay, so a typical point z, okay, on the image. Okay. And so that this one can be approximated as the sum, okay, f of z sub I, okay, and delta of z sub I here. So the meaning of this sum is actually, and z sub I, so you can find so z1 up to zn, okay? And the delta z sub I will be so would be the so you can do it so would be the difference. Okay, so you can okay, and the segment here, okay, and this is the z m minus 1. So that the delta zi will be a point. So z1 here, and so this is the alpha, say T0, gamma, and oh, by the way, this is gamma of Ti minus gamma of Ti minus 1. Okay. So this one is gamma T0, which is gamma alpha, right? And this point is gamma T1 and gamma T2. And up to here, this is gamma Tn, which is gamma beta. Okay, and this is gamma T minus 1, etc. Okay. All right. So this integral is the limit of this partial sum. Okay, and the difference, so that you have a line segment here, and you pick up a g sub I. So this sub I is a point, okay, in the arc, right, between. So the g sub I is in this arc, okay, right. And the difference, so the line segment can be approximated by this. So this is called the delta z, right? This sub I here. Yeah, this sub I. And if the division, okay, so the n goes to infinity, because if we take more and more divisions, then the chord or the line segment were very close to the arc, okay, right. And this difference can be approximated by the difference by using the derivatives, okay, with the ti and so that this can be, this one can be like gamma, and we can select an xi and ti minus 1 minus ti minus ti minus 1. Okay. So this is the delta t, okay, I. And the xi is a parameter in between ti minus 1 and ti. Okay. So, okay, and when the delta ti goes to 0, okay, this is become the sum, becomes to this Riemann integral. Okay, so that it is actually the line integral. If you, I think you may have learned this from multivariable calculus, okay, in your first year. Okay. Right. So that the reason why we define the line integral in this way is from this approximation. So this is indeed the function value f on the image of this path, and also weighted by the increment of the so that would be look at the fragment or the differential along this path. Okay, so that. Okay, so now we go back to our discussion here. Okay, so if we let gamma go to C, be a path. Okay. Right. So this is an oriented curve, right? And if we want to reverse the orientation, right? If we want to reverse orientation of the image, okay, if you want to go this way. Right. How can we do that? So that it will move from this endpoint to that one. Right? So one way to do that, is to define a mapping. So we define the map. So the path we call gamma tilde, which is from minus beta to minus alpha. Because beta is greater than alpha, so minus beta is less than minus alpha. Okay, so that goes to C, defined by okay, right. Gamma tilde t defined to be gamma minus t. Okay, so with minus t, now when t is minus beta, this is gamma beta, right? And when it moves to minus alpha, this is moved to gamma alpha, right? So the orientation will become this one. Right. So that this is called the opposite of gamma. Okay, so this is called the opposite of gamma. Right. So this, and so if f note that they have the same gamma tilde is equal to gamma star. All right. So they have the same image, right? Even though their orientation are different, but they have the same image. So if f is a complex continuous function on gamma star, okay, then let's evaluate the integral. All right. So we just change the orientation of the image, right? And so this will be minus beta to minus alpha, and f of gamma tilde of x, gamma tilde prime of x dx. Okay. All right, and by substitution, by this one, so this is minus alpha, minus beta, f. So we have gamma minus s. Okay, and the derivative. So from here, we know that the derivative of r tilde is the derivative minus t times minus 1, right? So we have minus gamma prime minus t and ds here. Okay? And now we, oh, sorry. Okay, now we let t to be minus s. So dt is equal to minus ds. Okay, and we have gamma t, and this is gamma prime t and dt. Okay, and because of that, we have beta to alpha here. Okay, and if we change the direction of the integration, so this is f gamma t, gamma prime t, and dt. So finally, this is minus of gamma f of z and dz. Okay. All right, so if we change the orientation, we find that the integral, all right, of f would change the sign. Okay, change the sign here. Okay. So for convenience, we denote, okay, the opposite of gamma by minus gamma. Okay, by minus gamma. Okay, so this will be denoted as minus gamma t. Okay, so minus gamma is used to denote the tilde here. Okay, so later on, when we know minus gamma, we mean this mapping. Okay, so the definition is gamma of minus t. Okay, and the defining parameter interval is from minus beta to minus alpha. Here. Okay. Of course, you can do arbitrary reparameterization, but this is the standard way to parameterize the opposite of a path. Okay. Any questions? Okay, so now we can evaluate some examples. All right. So now we evaluate the line integral in several examples. The first example, the gamma, is the positively oriented unit circle. Okay, i.e. gamma of t is equal to EI 2 pi t, and t is in from 0 to 1. Okay, so this is 2 pi t. So the center is 0, and the radius is 1. This is called the unit circle, right? Unit circle here. Okay, so now we want to evaluate so f of z is 1 over z here. And because we, the gamma star, the unit circle, right, the unit circle does not contain the origin, right? So that this function is continuous, right, on the unit circle. And if we do the line integral such that the path, all right, is closed, then we will use this sign, right? So we will write a circle here to denote that this path is closed. Okay. This. All right. Okay. So now we need a prong, right? So what is a prong? So a prong is I 2 pi and EI 2 pi t. Okay, so this is a prong. Okay, and so the integral from 0 to 1 and 1 over EI 2 pi I 2 pi t, okay, times I 2 pi times EI 2 pi t, okay, and the dt. Okay, so this, what is that? This is f of gamma t, right? And here is gamma prime t. Okay, this is gamma prime t. And our f, here f of z is 1 over z. Okay, 1 over z here. Okay, and so we have 2 pi I 0, 1 dt. So the 2 pi I. Okay. So the line integral is 2 pi I here. The second example, that gamma is the positively oriented circle with the center A at A. Okay. And the radius 0. Okay. All right. So now we evaluate gamma, right, and z minus a, m's power. Okay. And the m can be any integer. Okay, any integer. So now, we know gamma t is a0 plus rho. Oh, it's a plus rho e I 2 pi t. Okay, for t is in 0, 1. Okay, so this is the parameterization of such an oriented circle. Okay, it's there. Okay, and the f of z, as we know. Okay, all right. So dz. So we compute this line integral. And this is by definition. So now we have, so z minus a, okay, becomes to rho m and the ei 2 pi mt. Okay, and now the derivative. The derivative is equal to I 2 pi rho and E I 2 pi t. Okay. All right, so we have 2 pi I and the rho and the E I 2 pi t and dt. Okay, so we have 2 pi I, go to the m plus 1's power, 0, 1, and the e I 2 pi m plus 1 t and dt. Now, and we see if m equal to minus 1, if m equal to minus 1, this is 0, okay, and this is 1. So we have so we have 2 pi I if m equal to minus 1. Okay, so if m equal to minus 1, this is 1, this integral is 1, and this is rho to the 0 square, 0's power, so it's 1. So you have 2 pi I. But if m not equal to minus 1, and m is any integer, okay, is in z, okay, then this integral is 0. So this is 0. Yeah. Okay, it's very easy to see because the antiderivative is it's divided by I 2 pi m plus 1 and e 1 0, right? So when 1 here, this is 1 minus 1, so it's 0. Okay. Okay, so that this integral, this line integral is 0 when m not equal to minus 1. But when m equal to minus 1, then this line integral is equal to 2 pi I again, right? So all right, look at the third example. Okay, we consider fz to be the real part of z. So this is x. Okay, consider that, and we evaluate over 2 different paths. So gamma 1t xt plus 2it for t in. Okay, so this is so we consider 2 endpoints. This is 0. The other is 1 plus 2i. Okay. So this is 0. Okay. And along 2 different paths. So one path is here. Go this way. All right. So this is gamma 1 star. Okay. The other, we will check x from this way and go this way. All right. So this is gamma 2 star. So gamma 1, so it's the line segment join. So so this is t of 1 plus 2i for t in 0, 1. Okay, for t in 0, 1 here. And gamma 2t. Okay, so first of all, it will go from 0 to 1, right? So this is 1, right, horizontally. So this is t, okay, if t is in 0 and 1. Okay. And for t, the other is 1 plus I, t minus 1. So for t is in 1, 2, 3. Okay. So this is going up. The first part is move horizontally, right? And then vertically. Okay. So this is gamma 2. So we have 2 different paths here. Okay. Okay. And now we evaluate the same function. Okay. First of all, along gamma 1. Okay. Along this line segment. Okay. And this one, so this is the real part of t 1 plus 2i. Okay. And so we see that gamma 1 prime t is equal to a constant to I. Okay, constant. And for here, we see that gamma 2 is piecewise continuously differentiable, right? So you see that gamma 2 prime t is equal to 1. Okay, is equal to 1 for t in 0, 1. All right. And for here, we have I for t is in 1 and 3. Okay, open interval here. So it's piecewise continuously differentiable. Okay. Okay. So you can see we have, and so along this, so this is 1 plus 2I and dt. Okay. And what is that? This is 1 plus 2I, and the integral, the real part is t and dt. Okay. So that this is 1/2. So this is okay. So the value is this one. Okay. The other gamma 2 fz dz. Okay. So this will be the real part of t and the 1 and dt. Okay. So this is the first segment. The other piece is from 1 to 3, and the real part of 1 plus I t minus 1 times I times dt. Okay? All right, because the derivative, okay, in this piece is equal to I. Okay? And when you evaluate that, you will find this is equal to, all right, so this is 1/2 plus I, and here this is 1/2 plus 2I. Okay. All right, so that is not equal to, okay. So it's possible that even though these two paths, gamma 1 and gamma 2, has the same endpoint, all right, but has different images. Okay, so that around different paths, it's possible that but their integral will be different. Okay. Any questions? Okay. Now I will talk about some geometry of the Euclidean space, which will be needed in our discussion. So first of all, in the one-to-one correspondence, step C for z equal to x plus iy goes to y. In C, corresponding to a point, 2, right? So with this one-to-one correspondence, the geometry of the complex plane C, okay, has the same structure, okay, of as the geometry of R2. Right. So, for example, an open disk, okay, of radius R and center Z0, okay, in C, right, corresponding to an open disk, okay, of radius R and center x0, y0 in R square. Okay, so you have this correspondence. Okay, so basically, that the complex plane will be regarded as a two-dimensional Euclidean space. Okay, if we talk about their geometry. Okay, so open disk with radius R, with this center, but this center corresponding to a point, right, here in R2. So it's an open disk. And so this notation would be Z0 R. So this is Z, C such that okay, so it's this set and disk of x0 okay, this is here. And we also, there also call a neighborhood, right, of Z sub 0, right? And so this is also called a neighborhood of the point x0, y0 in R square in C. It's open disk. And also an open set, okay, omega in C, they're corresponding to an open set U. U actually is per C omega, okay, in square. And the definition of open set, as we defined, okay, in chapter 3, we say that for all Z in omega, there exists a neighborhood. Okay, so there exists a neighborhood we call delta, okay, of Z, such that is contained in omega. Okay, and also in R2, for all point x, y in U, there exists a neighborhood. Okay, right, a neighborhood, and called V, which is just per C delta, okay, of x, y, such that V is contained in U. So open set, closed set. All right. So this can be that defined in the complex plane or corresponding to closed open set and closed set in the two-dimensional Euclidean space, right? Okay. Now, so that now in general we consider, okay, in general a neighborhood of a point in Rn, okay, a neighborhood of X, an open ball, okay, an open board with center X and radius greater than 0. Okay. So the ball I use x0, right? So x0. Okay, so we call open ball. Okay, in general, because n can be arbitrary. Okay, so an open ball in the one-dimensional Euclidean space means that the real line would be an open interval. Okay, and this open interval is centered at the point. And if n equal to 2, an open ball is just an open disk. Okay, but in general, they will call open ball. Right, they call open ball there. So neighborhood of a point consider as an open ball. Okay, and a subset U of Rn is called open if for all points in U, okay, all right, there exists a neighborhood. Okay, there is a neighborhood B of X of X such that this open ball, this neighborhood is contained in U. Okay. Okay, so this is open set. Okay. All right. Now, a collection UI index of open set in Rn. Right. So this is a collection of open set in Rn. It's called an open cover of a subset X of Rn if we take the union of all open set in this collection, then X is a subset. Okay, so this is the open coupling. So if this is a set, okay, an open coupling would be a collection open set, so it is possible. Okay, and each one is U sub I. Okay, so that this collection, this open set will cover. Okay, it means that this way. Okay, so an open cover of a subset means that a collection of open set which will cover X. Cover X means that X is contained in the union. Okay, in their union. Okay. Now with the cover, now we will define a set. So a subset K of Rn is called compact. Okay, so compact is a very important concept. It's called compact. If every open cover of K contains a finite subcover. What do we mean? I.e., there exists a finite subset J of the index set I. So the index set I may be infinite, right? But we can find a finite subset J such that K is contained in the union of the open set, okay, indexed by this finite subset. Okay, so that means that a subset K is called compact. It's called compact in the n-dimensional Euclidean space. If any open cover, this open cover may be infinite, right? Maybe infinite. Okay. Now, then we can find a finite subcover. So we can find finite number of UIs from this collection, which will cover K. Okay. This is called the covering. Okay, covering. And compactness is an important geometric concept in analysis. So I will give a theorem called the Hahn-Borel theorem. Okay, a subset K of Rn is compact if and only if, okay, if and only if K is closed and bounded. Okay. So it's very easy to identify compact subset in Euclidean spaces. Right. If we check it's closed and bounded, then it must be compact. Okay. And compactness were preserved by continuous mapping So recall a function a function f from a subset x of Rn into Rm is continuous at a point x in S if for all epsilon greater than 0, there exists delta greater than 0 such that if that x in the ball x0 okay. So if this is R, we have x goes to m. Okay, so n and m may be different. And we say that this function, so f from x to m, is continuous at the point x0 if we find the image here, right? So if we select a neighborhood, which really is R here, right? So this is the open ball epsilon. Okay? So we select a neighborhood of the image of x0. We will select, so epsilon can be specified arbitrarily. Maybe epsilon may be quite small, but so for all epsilon, we can always find a delta. Okay? So we can find a delta. Okay, so we can find a neighborhood of okay, of delta, so that every point in this neighborhood will map to here. Okay. So there exists, so x in delta implies that the image is in epsilon. Okay? This is called continuity, right? Continuity here. So whenever we have, it's called continuity. So now a theorem. Oh, by the way, and intersect with S, okay? Because the neighborhood may be out of X, right? So we have to consider intersect with X. So the theorem is that a function is continuous on S if F is continuous at every point in S. Okay, so this is the definition. Okay. All right. So now I have to write two theorems. Okay, so the theorem is here. A function f from a subset of Rn to Rm is continuous on S if only if the inverse image okay, which is of any open subset U of the codomain Rm. Okay. So the image is the intersection of X and an open subset of Rn. Okay. So finally, so if F is a continuous function from a compact subset K of Rn into Rm, then the image f of k of k is a compact subset of Rm. Okay. All right, so compact set will preserve the compactness under continuous mapping. Okay. Right. So we need this result. Okay. Okay. So I'll stop here. Okay. And I will. So this part I will add into my lecture notes. Okay, and send you the revision.